Welcome to Chapter 11. This is Angular Momentums. I'm Sorasak Phanphak, lecturer from Kasetsart University. This is a part of 01420111 General Physics 1. Let's say we did learn a lot of things about the way that object was exerted by the force or not directly the force, some torque that exert to the system and make it rotate. And we did learn about the momentums, which is like in the linear momentums. If there are some impulse or the change of the momentums happens, that means there's going to be some force induced and involved into that kind of change. In this part, rather the object translate now the way that the linear momentum conserved also happened and similar to what we are about to looking after in angular momentums. The angular momentum is when the object have the angular velocities, also carry the properties and call the angular momentums. As I just said, force is exerted to the system and makes some impulse or the change of the linear momentums. In this case, if they have a torque exert into the system can change the rotational speed, which can change the angular momentums. And this torque is the cause of object rotate. Previously, we did state that torque is the quantity that we look only the magnitude of it, like torque equal to RF sine theta or sine phi. It depends on you define. In this case, as you can see in the figure, you have vector R and you have vector F, and the angle between R and F is phi. So this is our definition of torque, and we did state about only the magnitude of it. Somehow these properties, as you can see, the positional or direction is the vectors, and somehow we carefully look into only the magnitude of it. And F is a vector, but now we look only the magnitude of it. So how can we have this? Like they're gonna be a vector of R and F operate somehow, and the way operate we call it as a cross products. This is the definition of torque in terms of vector now. Torque is the resultance of the vector R cross F, which is R is point from the rotational axis. This is kind of like an axis. In this figure, you can see this rotate around Z axis. And with this, the direction of the torque itself is the result of the cross product. We will learn about our right hand rules. We have R, F, and then this is the direction of the torque. As we did mention before, torque is equal to R cross F. You can see somehow some textbook prefer to use torque like this, or you can write torque like this. It doesn't matter. It depends how you define it. And in this case, if you would like to define it as a vector, you can have the magnitude of it and directions. We represent N for the normal vector. Since R and F are vectors in the same plane, and you have N which is perpendicular to R and F plane. As I said, R and F in the same plane mean you can have R in 3 dimensions and also F in another 3 dimensions. But when you have R cross F, your resultant torque gonna point out in perpendicular directions like this. This is gonna be torque directions, which is perpendicular to both R and F here, if you look in 3 dimensions. So Since we come back to our definition of torque is equal to force with the distance that are perpendicular to the force axis. As you can see here, the perpendicular come from r sine theta. So this is d equal to r sine theta. This is somehow we use this type of information that derive from the vector operations. We will trace back to how we define the cross products and use that type of vector operation or vector manipulation of the cross product to find the torque. Since torque is the vector r cross f, vector r can be in 3 dimensions and f also can be in 3 dimensions. We will use the technique or method called the determinants. Use this way to find out what is the resultant vector of r cross f. And as I did said, torque is in Newton meter unit, because if you look here, r is in meter, f is in Newton, so the unit of torque is Newton meter. But again, torque is vector, so now we will operate this torque as a vector. The vector product is how we use our right hand. If you're not familiar, the way we use right hand not only for mechanics in the electrics or electrodynamics, we can use this for predict the directions of all properties that come from the cross products. For example, if you have vector A cross vector B like this, like in this figure, you can stretch your palm out, and this direction is the direction of vector A. And when you cross it, that means you wrap your hand toward the direction that another direction vector cross with. So A cross B, and the thumb directions is the resultant vectors, the direction of the resultant vector. So that I call it N, which is normal to A and B that cross each other. However, if you have B cross A, it's different. That means you have vector B first and cross back to vector A, and the direction is pointing downward. So the direction is opposite if you have the different order of vector in the cross product. As we did state that vector A cross B is equal to AB sine theta in terms of magnitude here. And the direction is according to the right hand rules. If we know that what happened in 3D, for example, if this cross happened in X and Y, so when you cross it, it's point out into Z directions. So vector N can be K, for example, if in this case. However, we can do determinants to operate and find out the direction later. Somehow, if you look only the magnitude of it, in this case, the magnitude of vector A cross B is AB sine theta like this. That means if you have vector A pointing like these directions and vector B pointing like these directions, and this is the theta between A and B. What is A sine theta or B sine theta? If you said that, okay, you would like to have B and A sine theta, that means you will have vector B and A sine theta like this. This is the area that you multiplied it. Also the same with this. If you would like to write down like A and multiply with B sine theta, what you have vector A and another B sine theta, and this is now in the not trapezoidal, but my fault, I will write it properly. What you have here, you will have the one that rectangle with the right angle here. And this part is your B sine theta, and this is A. All you have, this is the area, is this area of the space. Right? If you would like to determine this area, this two area, you can have A, B sine theta, since this angle is the theta. Or if you don't know the theta, you just have the cross product and find out the magnitudes of A and B to find out this area. We will learn this part through the example and understand how we operate on the cross product. But remember, in this case, the way to have cross, we're going to apply with R cross F to have the torque in terms of definition of vectors. This is our goal. We state about the property. So as I said, A cross B is not equal to B cross A. So that you cannot use a commutative law. You cannot swap the order between A and B or B and A. When you have A multiply cross A B, if you would like to switch order, you have to have the magnitude with the negative signs in front of it. It means A cross B, you have upward directions. B cross A, you have downward directions. You change the order or change the directions. That is lead to, if you have the same vectors crossing each order, that means you have vector that pointing into the same directions. So you have sine theta that equal to sine 0, so that it's zeros. As same as if you have another directions and still in a parallel, that means you have sine theta that equal to sine 180, which is also 0 as well. Not only you cannot do a commutative, but thing is, the way that order change is effect, but you can do distributive, like you distribute all the quantity that's multiplied with out. Like for example, A cross B, you have A cross B plus C inside this bracket. You can have A cross B plus A cross C, like this. And also all these also can be applied by the right hand rule as well. You can have like A and B as a resultants vectors, and then you have A cross that resultants. You're gonna have the results of the cross product as well. Also, not only the distributive in terms of the plus each order, when you using the derivations of in terms of this cross product through the vector A cross vector B, you can have the vector A cross B plus A cross vector dip vector B by dt as well. So this is how you can use the properties of the vector products, and you can apply in the later section. For example, if you like to find the torque, you can use these properties and you can operate with the vector operations. Not only that, the vector products also can be used with the unit vector as well, because we have to do the part of the distributive law. That means if you have two vectors like vector A that have I and this is vector A, you have AX, AYJ, for example, and you like to have this one cross with vector B, BXI, BYJ, like this. You can do a distributive, like have A multiplied with this term, so you have AX, I cross I, which is this is the BXI. As you can see, vector I gonna cross with vector I, And this means they are in the same directions. So I cross I gonna turn to 0. It's exactly the same as j cross j gonna equal to 0 and k cross k gonna equal to 0 because vector in the same direction or in the parallel directions equal to 0s. However, when two unit vectors are perpendicular, they're gonna have the maximum value, but the directions gonna change according to the right hand rules. If you have I cross j, you got k. If you got j cross I, you got minus k. But if you have minus in front of it, it's k. If you have j cross k, you're gonna have I. If you reverse order, you have to put the minus signs in front of it to have the same. This is the same in not only I cross j, you can see the j cross k or k cross I, you can have vector as a resultant vector according to this diagram. If you cannot remember, if you have I cross j, what you got k. If you have k cross I, you're gonna get j. But if you do reverse order, if you do k cross j, you're gonna get I, but with negative sign. If you have the j I cross k, you're gonna get j, but with the negative sign. This is how you using the properties or identities of the vector products, and you can identify the resultant vector from the unit crossings product. As I did state, if you would like to switch order, you can have the negative sign in front of it. But the negative signs can be interchanged since A cross B is the resultant product. So you can have negative signs in front of A or in front of B. Also, exactly the same as the unit vectors, whether you would like to have in front of J or in front of I, they are exactly the same. The way that we can calculate the cross product, we can apply the determinants law for using. This is the method, like mathematical method. If you cannot remember it, I revise it here, and then you can use it for finding the cross product, or maybe later about the angular momentums. How we find the angular momentum that link to the linear momentums. We can also use the cross product to quantify it. So if you have the vector A and the components in 3 dimensions, like AX, AY, and AZ in direction of I, J, K, also vector B as well, and these two vectors are crossing each other, how can you find the resultant vectors? So the way to write down, you can write the individual directions in I, J, K, and if you have vector A cross vector B, you insert the components of vector A in X direction, AX, AY, and AZ here, right? How about B? You insert BX, BY, and BZ here as well. Then you can cross it maybe using the minor or cofactors to cross it like this. This is how you generate it. If you would like to have I directions, you cross it. So you have the determinants between AY, AZ, BY, and BZ components here. And if you like to have the minor or cofactors of the J components, you look after J rows and you cross it out. That means in determinant you have AX, AZ, BX, BZ, like this. Now you can just do determinants directly. Or if you'd like to have only K, when you cross a row that binding to the K, so you have x ay bx by like this. Somehow this way gonna be more simple for some people, but you have to write down a lot of things. But the way to do determinants, you have to multiply the crossing rows. So in this part you have a set by, and this part you have a y b set, and the upward the upper rows you have to have the minus sign in front of it. So this part you have a y b set minus a set by like this. It's also exactly the same like this. You have ax b set minus, and the row one you have a set and b set in the j row. Sorry, this is I think bx. Right. These are all what you can do when you separate minor and cofactors. However, I would suggest you to do another way, and this one you can do on your own, and we check with this formula. You can add another additional rows. For example, like if I would like to add I and j, because the way I cross, I would like to cross all three components here. So I will have the ax, ay, and bx and by here. Since when you cross it, you multiply all these together. So this part you have a, y, bx, k directions. This is the components of the k, which is this one. Another rows, I'll multiply this part. So I got a set b, y in I directions. So I got these components for this part. Another rows, I multiply these. So I will get the ax b set in j part. So this are component of this one. The upper rows, as I did state, you have the minus signs in front of it. It's exactly the same as the lower rows. So if you would like to determine it, so I will draw like this part. So I've got a, y, b set for I directions. For this term, I got bx, a set bx, sorry, a set bx in j directions. And for this term, I got ax by in k directions. So these are all these components that I get it out here. So it's depend on your preference. You can use the method that I use it, or you can use the minor or cofactor to find out the determinants. Now let's look into this problem and how we can find the torque out of the way that I propose about using the vector operations or cross products between R cross F. So as you have known, so you can do the distributive on all these terms, like you have R, so you can write like R cos F in terms of R here and F, and then you do all distribute, like first term multiply with the first term and multiply with the second one, the second term of R, multiply with the first term of R, and then the final term. What you have seen here, thing is, if you have I cross I like this, or J cross J like this term going to equal to zeros. And what matters is I cross J, which is K, right? I, J, K. And J cross I is a minus K. Here is minus K. So finally, you only have k terms of this is like 12, and then you minus with 10 here in k directions. And this is the answer. If you would like to find the torque from the definitions of the cross products. This is our first method. How about the second method? We can use determinants to find out about the torque. So let torque equal to R cross F, and then we have that out of IJK. Remember, even this system have only 2 dimensions, but the cross product gonna be in another planar. These R and F look like they are in R and F. They are only in XY plane, right? Oh, sorry. Write another color. So they're only in XY plane. So R cross F, you're gonna have another vector point upward. So this is n vectors. This is the unit vectors of R cross F. To find unit, you have to divide by the magnitude of it, right? So that's the reason you have to put all the components in. So how about R in the first row? We're gonna substitute the components of R. So it's 4, 5, and 0 because IJ no K. And how about the F1? So it's 2, 3 zeros. And you put J in. This is 4, 5, 2, 3. So now you multiply all these terms. Like here you got 10K. This term got zeros, right? And this also got zeros. How about the lower part? This is zeros, this is zeros, and this is 12K. This is zero. So finally, you will get the above one with the negative size. So the torque is equal to 12K minus 10K. So the final answer is 2K in Newton meter. So this is how you can find out the cross product, and this is the result of the torque from R cross F.